And we should be streaming for the 4th time. Epic! And I have Johnny here with me. I like to do the Lion King scene with him sometimes. And he's a 24 degree of freedom humanoid. That means 24 servos. And he's pretty capable. I've covered a lot of things in previous streams. And I can get him to say hello. Maybe from another view here. I got down here. I'm using the PlayStation controller to get him to say hello. And I can move him around. It's slippy on this table. Be careful here. He's slipping. And move his head left and right. Up and down. Now he's looking at the camera. Give us a wave again. Cool. So that's Johnny. So I have a big plan for today's stream. If you move this camera to the top. Cool. I have this new t-shirt actually I wanted to show you. It's from the Humanoids 2024 conference that I went to in Nancy, France. I like the back. I think it shows that. It shows a robot drinking coffee, maybe? Cool. And as I said, this is the 4th stream. I did 3 streams before. November 12th was when I was unboxing Johnny. Covered a lot of things down here. It's all in my public Notion page here. That was a hell of a day when I was unboxing him. Then, oh no, I've closed. Excellent. You're not seeing what I'm saying. I was saying unboxing Johnny here. I had the first stream on that. It's all on my YouTube channel as well. And the second stream, I was running more of his code, what he came with. He has an app, PlayStation controller, showing again all his servos, degrees of freedom, different actions he came with, and how we can program him with tmux. Last time I covered, it was last Sunday. I'm trying to do this more frequently now. Last time I covered soccer playing, and I was making analogies between soccer and sock picking. How typically in robotics and AI we can approach things like similar tasks with similar approaches. So visual servoing was one approach. That's what I'm getting a lot of success with at the moment. But another approach is like the classic sense, think, act pipeline, motion planning, state estimation, control. There's also pure reinforcement learning, what DeepMind did for soccer. Talked about that last time. And then there's a whole other approach, which is actually the most successful when it comes to humanoids and them being useful in our home and in factories, is imitation learning. So I covered all of that last time. But this time, let's see what the plan is. So I'll make some space here. And as I said, I'm going to try streaming probably weekly. Let's see how I succeed at that, because it requires more planning, but there's less time to plan, less time to code. Maybe there'll be more randomness coding live, but at least I have a bit of a plan for this session. For a while, I was a little worried about Johnny. I thought something was wrong. I thought something was wrong with the hardware, but then I actually found out it was just one very subtle bug. And like a father with their son, when they're sick, you just get worried for your son. But I'm so happy he's fine now. Then it was just a software bug that I introduced, and this is why we have Git. I could show the before and after by checking out a specific commit and seeing he wasn't able to walk properly after a certain commit, but before the commit he was. That's why we check out code at different levels. Cool. But yeah, that's not really the focus for today. One kind of thing that'll put everything into context, what I want to talk about today, which is simulation. So Unitree came out with this video, and they're coming out with videos every few weeks. Now it's got this sassy hip walk, and it's running the G1 humanoid. I just want to repeat that sassy hip walk. It's like, it looks way more natural, like the swing of the legs. And running on rocks, that's very impressive. Up hills. Down hills. Steps. Catching falls. The sassy walk again. I wonder what meters per second that is, but I would guess over 0.4 maybe. Two of them. I think they're actually selling them now much more often. I'm seeing much more labs have a G1. Therefore, costs will go down. Like in 2025, I expect costs to be below 10,000 soon. $10,000. But anyway, this Jim Fan, I'm a fan of Jim Fan. He works for NVIDIA and in the kind of humanoid lab in Groot, they call it, I think. Like, number one, he's saying to reverse engineer this, you need to treat simulation as a first-class citizen, because if you can scale and do reinforcement learning in simulation and it transfers to the real world and it just works, then motion capture, that's such a benefit of humanoids. People often ask why humanoids, and I could talk for hours about why humanoids. And yes, you could have 10 fingers, why not 4 arms? So many arguments on every side, but at the end of the day, even if you just copied YouTube data or triple A games, movies, everything, we have a lot of movie person data, people doing things data from third person views. It's a treasure trove of data. It's the $1 trillion question. How can you use all that data to then make humanoids do things? And I think we will unlock it. There's already some signs of that. And simulation, like, it used to be this kind of thing you did after building the hardware, but it has to be part of the design process. How do you simulate well? I'm not sure if Johnny simulates well beside me, but Johnny simulates well, but we'll keep trying to improve his URDF file. Like co-design, because if you can just do large scale PPO, throw in a bunch of GPUs, and you have like a million humanoids running around in simulation on rocky ground, and then you just do sim to real and it just works, you get this. As he walks, running on, like, I even find it hard to run on ground like that. So I think the world is not ready for what these humanoids can do. Anyway, but that gives a bit of context for why simulation and why it needs to be a first-class citizen. So that's what I wanted to talk about today. Now I have many different scripts and things to talk about within here, so we might as well get started. One, I can talk about a bit of the pink and visualization tools. They're not really simulations like meshcat and URDF. Let's jump to that first. Okay, so I have my thing here. Let's open a terminal. Let's make this bigger. Ainex. Got many files here, and we can run the pink load custom or pink visualize in URDF. Let's activate my proper conda environment. So pink is an inverse kinematics library, but I'm just mostly interested in the visualization at the moment. Cool, so this is from the Caron guy. He built this robot in the real world and also simulated with pink, and he built pink the library. And he's doing an inverse kinematics challenge here, kind of like a squat for this robot. So that's kind of a simulation, but it's more a visualization tool than inverse kinematics. Let's see if we can load in Johnny. Let's go pink load custom URDF, which I should have set to Johnny. It's loading. Yeah, well, there's Johnny. Let's see, Johnny's here. And he's here. But there's not much I can do with this tool. I can do some kinematics, and I was changing the color of his shoulder joints just to make it easier to see. Black is a bit hard to see against certain backgrounds. And change the color of his gripper as well. The right gripper is what I usually use to grasp objects. So that's kind of cool, yeah. You can visualize. I can show some of this code. Custom URDF, and we're using Pinocchio actually, not even pink. We're just building from a URDF file. Everything is just URDFs. And we're able to use URDFpy to visualize. I can show the Johnny URDF file, which is really the basis for a lot of simulation, is just to have a good file to describe your robot. Material colors. This is more for gazebo. I don't think it's relevant for pybullet. Hardware transmissions. Then you have your links and your joints, and joints connect between links. So my forearm, for example, connects to my elbow joint, and my elbow joint can have a certain angle, but my forearm just moves with the joint as at a certain angle. That's how we specify humanoids, how we specify most robots. Joints and links, joints and links. And there's a lot, as you can see, probably 24 degrees of freedom, so 24 joints. I'm not sure how many links. I can count that. Then we have some other gazebo parameters down here. Cool, so I can also show the meshcat. So here's using pink and Pinocchio. Pink is built on top of Pinocchio, and we can actually visualize what's the name of the file? Ainex meshcat crazy design movement. So this time it's actually going to use meshcat to open a Chrome tab, and I'm just doing crazy sign movements of Johnny. But again, this is not a simulation. There's no self collisions. There's no ground. There's no physics exactly, but it kind of looks funky and cool. I wish I could do this. Cool, so that's pink, but these are not really simulations, as I said. They're like visualization tools. Pink is a inverse kinematics library built on top of Pinocchio. which is a rigid body dynamics library. Anyway, there's so many simulations that you wouldn't believe. Some of the most famous, though, are mujoco. I need more experience in this. It's quite deep and complicated, but I have some. Genesis was released in December. It's very impressive, high quality, and you can like a generative simulation, so you can build your own scenes with just text prompts. Still a lot of work for it to be better, and it's also very fast. Isaac Jim is also very fast, and you can put 10,000 humanoids like what they did in this video. First, they trained this in simulation with crazy grand, and then we're able to apply it to the real world. And with GPUs, you're able to, in parallel, train 1,000 humanoids in one environment or pair environment to do locomotion, grasping, everything. And there's many other simulations I could talk about, but this field has kind of changed over the years. I even wrote a blog about it in 2020, From Cups to Consciousness, Part 2. I was even using the AI to Thor. This is my repo with my colleagues from MTank, our old company. We were running reinforcement learning with Rainbow DQN and A3C, and A3C gated attention for certain tasks like pick up multiple cups in a bathroom. And we had this blog, From Simulation to the Real World, that we wrote in 2019, well, a lot of time ago. And I was using pybullet here to simulate this vector robot. The company died, Enki, the company died, and we were simulating all the cups falling and vector robots fighting each other. And we called it Cup Carnage. It was like a game. A simulation is like a game, but it has physics, and it's more about accurately representing physics. And you can see why it's Cup Carnage. One person's taking the cup to the horizon. 20 versus 20, or 10 versus 10 vectors. Then I load the cups once they're just about to crash, and it's all out war. But anyway, in this blog, I might as well link it. We had some cool quotes from Joshua Beck and comparing different environments, but this was AI to Thor in 2019. Things have kind of changed a little since 2019. Mujoco was open sourced. Here are two real vectors we had with a real cup. You can also do gazebo simulations and the moon, scoring goals. And this was round 2, 20 versus 20 vectors. This was all created with pybullet, so my experience is pybullet. So far, I love how simple it is. We were comparing different simulations here somewhere. Or maybe not. Maybe it didn't have that table, but there's a lot of tables showing many different simulations. I'll mention that blog here. Anyway, many simulations, but let's focus on pybullet. It's because it's so easy to use, and I love it. So let's load many robots. Let's see. Here I'm loading an arm, a quadruped, animal quadruped, Tiago Talos from PAL Robotics. I don't know what robot that is. And that's just some torso. And then I'm going to activate gravity. And some fall through the plane. Must not have proper physics set up. telos just completely falls down. And with the mouse, I can actually grab any of these models and let physics happen as if it's rotating around my mouse click point. I have no idea why Telos, or this is Tiago, is losing its mind and why gravity is affecting it weird. But every kinematic link and joint here is controllable. So I'm dragging up, dragging down, dragging up, dragging down. I don't know why it's losing its mind with this box, but I can kind of force it to be here and move it around. Let's grab another quadruped. Sliding. So that's how we load many robots, but they're all falling over and not really actuating themselves. I don't know why Tiago's in the sky, but I can show you how the script worked. So, load many robots. Many different robots we can get from the load the robot descriptions GitHub repo. But these were just some of the ones I was loading. If I loaded more, the file crashed. Maybe some files are not good enough. It's very common for URDF files to not be good. Then I'm loading them into a grid with a certain amount of meters between them. I'm using the load robot description function. And I can set fixed space true, so they either stay where they are, so they don't fall. Whereas if you use fixed space false, they will fall and they can move around as I showed. Cool. That's how you load robots and how you load many robots. And I kind of talked about Ainex's URDF already here. Some changes I had to make because what came from the company Hiwonder, it wasn't correct. File wasn't correct from Hiwonder. So some of the changes I made here, I had to rotate the shoulder by pi over 4, so 90 or 45 degrees. Shoulder pitch joint, so it didn't begin in the right place. The real robot would begin with the hands, kind of the palm, the top of the hands pointing toward the ceiling, but the simulation would begin with the top of the hand pointing to the ceiling, but the real robot would kind of begin at an angle. So that's why I'm rotating this by 45 degrees. I also had to invert the axis. I think it's just such a silly mistake. I'm just trying to copy the real robot, so the simulated robot acts the same as the real robot. Also had to invert the X of the shoulder roll. Again, 45 degrees. Here I'm changing the material colors so it's easier to see. That's why the blue shoulder pitch links, or yeah. Cool, so can we simulate Johnny a bit? Yeah, we can do teleop sliders Johnny here. So how does Johnny, my humanoid, look in simulation? I have a teleop slider kind of thing here. I really regret choosing an AMD GPU. I wish I had an NVIDIA GPU to run way more things. But oh well. No, he fell. Let's pick him up. Can we get him onto the ground? Yes. I have him in this kind of deep squat grasping position. You can turn the GUI off and on by pressing G. And I have these sliders. So we can change, I can't see the first letter here, that's the pybullet bug, I think. But we can change, nothing's happening there, wait. The gripper, yeah, I'm closing the left gripper there. See from this angle. So minus 0.9 is completely open, 1.4 is completely closed, even going past. Shoulder, that's the right shoulder there. Change the shoulder to be there. So this is just teleop slider based control. It's a very common thing for me in robotics. And you can change each of the angles, and you can see physics is actually happening. So if I went too fast, whoops, my mouse lost control there. But you can see it's causing dynamics to happen. I just changed the hip pitch by accident. Can we get him to stand up again? Nice, we're back in the squat. I meant to move that really fast. You can see if you move your hand really fast, it causes a dynamical force. That's what physics simulations are trying to accurately model, I suppose. Elbow yaw, it's the left elbow yaw, left elbow pitch, left shoulder. See how fast we're moving here? Just using the hand, we're creating a force. Left shoulder pitch. And we don't have self collisions, I don't think. We can prove that. Yeah, you can see the blue going into the black part of the chest. Knees, it causes the robot to almost do a backflip there. That was cool. Ankle pitch, right ankle pitch, I think. Hip pitch. And so on. Yeah, so 24 degrees of freedom. In this file, let's look at the file. I'm creating sliders for all these joints. I have a function to create a table and with different objects, but we're not showing it at the moment. Trying to get a better system identification of the gripper, but I'm struggling. There's problems with the gripper in simulation. And here's how we load a robot again, is this p.load URDF, the specific path. And I'm saying use fixed space false, which means it can move around, it's not stuck in one position. Sometimes it's useful to have both, one or the other. This is how I step the simulation 100 steps. And I'm creating joint sliders, and I'm beginning him in this kind of deeper arm squat. This is simulation. The whole point of simulation is to enable faster development. At least that's one reason. So I can then test the deep squat or a grasp in simulation, see if it looks good in simulation, and then apply it on the real robot, which is also safer in case something goes wrong on the real robot while I'm just testing. Here I can just break the robot in simulation 1,000 times and not worry. I'm updating all the joint positions to the slider positions. There is some limitations to pybullet, so I had to like remove certain sliders and then add them again. That's why some of the sliders weren't working, because I had to add them later. Some limitations with pybullet, but it's still good and simple to use. And then here's the main loop. We're just reading all the slider values and then setting p.set joint motor control. This is one of the most common functions in pybullet. We're choosing a specific robot, a specific joint, what type of control, velocity, position, torque control, and we're setting a target position with a certain kind of force. And that's how we get a certain joint to go to a certain angle. That's what position controls means. Just in radians, we're going to a certain angle. And we can also read keyboard events like Q for quit, O for opening the gripper, C for closing the gripper, and different presets. And generally what then happens is we just step through a simulation. You can step without sleeping, but you kind of want to see what happens, so that's why we do a sleep right after. And then we disconnect. So that's teleop slider. We can maybe show the same for G1, the robot, the same G1 that was in the video I showed earlier. So change AI next to G1, teleop. So this is the same robot you were seeing in the tweet. This robot is right here. I have the simulation. No material colors or physics or anything like that, but it's really cool that he's here standing. And of course I can, maybe fixed base is activated here. So now I can't lift him. Let's prove that. In the code. So this is a much simpler file here. We're loading robot description. We're not doing p.load, but it's the loaders from pybullet, so it's doing p.load underneath, and we're using fixed base equals true. That's why I'm not able to move him around. If I set it to false, I will be able to drag him and throw him around. So let's see. Now that he's fixed, I can actually move every single slider. Left hip pitch joint, left roll joint, yaw joint, it's like femur rotation, knee joint. Humans can't do that. I don't think so. Ankle pitch, ankle roll, hip pitch. Yeah, it gets actually stuck on the ground. You have to have enough force to get through. Yeah. But yeah, same kind of things for the left foot. This is why this robot is able to roll itself into a ball, as they showed in their first video. Be easily packable and deployable, transportable. Again, hip joints. No self-collisions here again. So we can go through the arm. But self-collisions are really complicated in general in physics simulations. Roll joint. Torso joint. That's really cool. Where were we? Torso. Left shoulder joint. Pitch. So upwards. Left shoulder roll. We can go through the body there. There's no self-collisions. Left shoulder yaw. So yeah, 3-axis shoulder. That's what humans have. Elbow pitch. Just we have elbow pitch and elbow roll. That's interesting. Humans just have pitch, I think. It's my understanding. But there seems to be very few joints in the wrist, so that's one way to do that. Add it to the elbow, and it's better to have more actuators in the elbow rather than in the wrist, otherwise torque is a problem. If you're carrying things very far away with like heavy objects, it's much harder to hold an object here than here. And here it actually has this default hand has like 6 different joints in it to affect. Probably has you can rotate the thumb to point different angles. You can then close the thumb a little. Then there's also another part of the thumb. That's really cool for pinching. There's let's call it the index finger. And again, each finger has these 2 ways of closing, similar to our fingers, and we can grasp like that. And the other arm, the same for the other arm, the right arm. So shoulder pitch roll joint, pitch roll yaw joints, elbow pitch and roll, and then 6 or 7, actually counting 0, 7 degrees of freedom in just the hand alone. And we can, one day hopefully I'll be talking about hands more often rather than simple grippers with just parallel jaw grippers. It's just this. I like to make jokes all the time that often robots are just grabbing things with their grippers like this. But one day it would be nice to have even 20 degrees of freedom in a hand. And it seems like Tesla has that many degrees of freedom. I have to double check the numbers. So yeah, humans can't do this, and because I've set fixed space to true, it's not falling over. So it's a nice way to see all the joints. That's a cool non-human position. Nice. I should have showed a wireframe mode actually. So we go here, click the wireframe, see all these meshes, polygons that represent every part of the robot. I press W to go to wireframe mode. And yeah, there seems to be gaps in the physics. We have to simplify sometimes to make simulation even feasible. It's really hard to simulate. And I talked about this function p set joint motor control 2. And we should also talk about forward kinematics. I mean, maybe in general, I should just describe forward and backward kinematics. So kinematics, forward, where is my joint or link XYZ and full pose? That is XYZ and rotation, 3D rotation. Forward kinematics, shortened to FK. Inverse kinematics, shortened to IK, is if I want my end effector or joint or link to be at XYZ rotation and rotation, what angles do I need for each of my joints? Pybullet has this by default. We know where every single joint and link is, full pose. So it does have its own inverse kinematics function, but it's not so good. So we need to try many other ways of doing inverse kinematics, but we'll come back to that. Anyway, to get a link state or a joint state, to get link state, but we also should look for the getting a joints state. Let's see if I have that. All actions. Yeah, get joint state right there. That's the angle. Just like that, we're able to get the right shoulder's pitch angle. Joint state. And using this, you know exactly where your robot is in space. So that's forward kinematics. Inverse kinematics is what angle do I need for all of my joints to get my hand around a cup, around a sock, around the target object. Even for my legs, you need inverse kinematics. So where do I put my feet to not fall over and to actually have a good walking gait? Okay, so I've covered a bit of pybullet intro. Again, my URDF file I talked about already. Let's close some files here. Large file specifying all the properties. Now, I just have to try to trust that they have done the inertia matrices correctly from their CAD. I'm hoping it's correct, but it's a really big pain for me to optimize these inertia matrices. This specifies, in some sense, how much weight is in a certain part of each link, how it's represented, if different objects would have different inertia matrices. So, for example, this object is a complicated multi-link thing. This is a camera holder. In my real sense, actually has a joint to change between these two links, but there's a lot of weight in the real sense. So you need to represent that a lot of the inertia is here. The torque of this, it'll move differently as compared to if the real sense was in the center. So this is how we represent dynamics with inertia matrices. And that's complicated. I hope I don't have to do that for Johnny. I hope Hiwonder, the company, did well. But we'll get to actually comparing the real Johnny to the simulated Johnny soon. So what's next in my scripts? So I showed you the teleop sliders for Johnny and G1. Let's have a little look at camera control as well. Camera. Fun. Here I'm actually moving his head. And we can see this takes a bit more processing. We're not as fast once we're trying to create synthetic camera depth and RGB and segmentations. You can see his head moving, looking around, and I'm actually simulating, based on where his head is pointing, what he would see. Maybe one day I can use this to simulate a full sock picking application. Here I think it's BGR instead of RGB, but you get the idea. It'd be quite hard to simulate a full sock picking application. We'd also need some soft objects, which pybullet has the capability to do, but I haven't run it yet. So that's camera fun. Do I have the camera controller? Let's see. This is R2D2 kind of looks like. And here again we're creating synthetic RGB camera data. I think I can press O for orbit of the camera, so you can completely control the camera to do anything you want. And I can press P for printing the current camera parameters, position, distance, yaw, pitch. Can try to control the camera while it's orbiting. No. Reset the camera to a specific place. That's not working. Start again, and if I could press reset. Nah, reset. Oh yeah, if I zoom out and then press OR for reset, it goes back. Cool. I always have to press Control to rotate around, and I press the middle mouse button to, and with Control, to kind of pan around like this. Many different softwares have different ways to do panning versus rotation. So that's the power of cameras and control, and this is how we would simulate data for the robot to, for example, pick up socks or some other application. Okay, then we're getting now to comparing the robot, comparing the simulated Johnny to the real robot. So let's see this script. A lot of stuff in the script, a lot of to-dos of how to do proper system identification, which is pretty much just trying to make your simulation more closer to the reality, how to change the URDF file, and also simulation parameters and many other things. And I'm even trying some real-time simulation here. So p dot step does nothing. P dot step simulation does nothing. It's just everything's running in real time. So let's see. Many different actions. I had to convert all the actions in pulse angle PWN format into radian format. Multiple action lines and all these files. They're in JSON now. I had to then. Now I'm able to then run these actions in the simulated robot, and we can compare what failed, what didn't fail. So in the beginning, I had no PID gain set in this function, and we can show how even the most basic functions, basic actions failed. So I'm going to comment this position gain. Let's make all of this bigger. I'm commenting this position gain, and if I run Python pybullet Ainex comparing to real life running all actions. I put this text here. You can have some debug text. It's kind of cool. So the current action is greet. But as you see, every time he moves, there's a lot of shaking in the feet. Or in the whole body there. So greet is the one that always worked. It's the same greet that I can show on the real robot here. Obviously, there's something not aligned with the speed between real world and simulation, but the motion, the correct joint angles are correct. So that's great, that worked, but then I quickly found out that every other action didn't work. So let's try some of the others. For example, even just raising the right hand, he fell over. Just like that, I'll run it again. Raise the right hand and down. Of course, then things like kicking with the left foot, of course would fail. Completely loses balance, and I always love doing this. Can't do this with the real robot. But yeah, he's repeating the action of left kick there, even on the ground. See, I'm getting 9,000 FPS. Not bad. Pretty much, yeah, everything worked. Walking backwards actually, everything didn't work. Walking backwards did work. But yeah, something's really wrong since everything kind of failed. So then I just was changing the PID gains. So even inside a simulation, there's a PID or even a PD controller for how fast each joint angle should get to its desired set point. So I had to tune it a bit. I tried many different ones, but this finally made way more actions work. So let's go back to the raise the right hand. Much smoother rather than quickly going there. So that works. He didn't fall. Not bad. Let's run. I know greet will still work. What about left hand put clock? You reach. Yeah, not falling. It's putting the block. Cool. Let's try the left shot. I think that's still gonna fail. Kick. Already it's falling, so maybe just too slow to kick. Or something's wrong in the inertia matrices, something's wrong in the physics, something's wrong in the URDF. It's really hard to do system identification, but I could do a mass nonlinear optimization to find the correct parameters to make it closer to real world. Because we know that all these actions in the real world don't make the robot fall over. So we have the ground truth of success. All these actions should make the robot not fall over. That is some form of an optimization, but complicated. And I'm not sure if it's worth it. Well, it could be worth it, but so, and of course hurdles fail. We saw that in stream number 2. That's the really long walk and balancing operation. I don't know if you can balance on one foot in the simulation. That'll be hard to get correct. And it completely falls over. But many more are working now since I said it. I was writing a comment here. Which other ones failed? For most impressive to me was that actually we're able to walk forward, because that's mostly what I'm doing in the real world, and this is the beginning to like walk forward, turn, and do things in the simulation and the real world that are close enough. So walking forward works. Amazing. Now it's the action of walking forward, is not the gate manager's way of walking forward. But still good enough. What about rotation? Let's see. We're running these actions in a loop, by the way. So turn left a little, go forward as well. Yeah, he's like rotating his hip yaw a bit to get to the left while also going forward. Fine. Maybe there's a bit of slippiness on this ground as well. I'm not sure if I need more friction. Let's see. Calibration, what's this? Yeah, this used to make the robot fall, I think, but now we're good. So we're closer, but it's still very complicated to do system identification. And it comes back to like Jim Fan's tweet that there should be like a co-design, a hardware co-design. You should just make your hardware like simulation be a first-class citizen. You just need to simulate well, and it's not simple. I could optimize the URDF since the Hiwonder, the company, didn't do good enough of a job. And I don't want my robot falling 10 times more in the simulation if I ever want to do human mocap stuff, because it's just not an accurate simulation of the robot. Cool. What's happening? Cool. So kind of compared to the real robot, talked a little bit system identification, which I'll define as making the simulation behave more like the real world. That is changing URDF, inertia matrices, physics simulation parameters, as we saw the PID gain, the PID gains, better friction dynamics. And I've created a script called pybullet Ainex walking, so I can try to work on legodometry. That'll be awesome. Ainex walking. So it's the same walking you saw before, but here we can try to create some form of legodometry because we have the real position of the robot, the ground truth position in the simulation of where the robot is. I mean, you try to create some form of a legodometry. Even if it's really wrong, it's better than nothing. And we're walking in this direction, so let's say we've traveled half a meter already, if these squares are 1 meter. Half a meter in the x direction. These axes, blue is for Z, green is for Y, and X is for or you remember that as X, Y, Z, or G, B. So yeah, we must have traveled a meter now, just about. I'm happy that walking works at least. There's other problems. The gripper is not able to grasp things in the simulation, and I'm finding that very hard to model. Maybe I'll just need a simplified gripper in the simulation that is not as accurate as the real world gripper, but it works. It is able to grasp things in the simulation. And it's an action, so it's like a keyframed based walking action that you're seeing there. Typically in Johnny's code, there's this gate manager class that specifies how fast you want to walk forward, how high should be the hips, should it be a low squat like a crawl versus standing tall, and how much rotation, how much yaw rotation, and also how much strafing, horizontal movement. You can specify all this in the game manager. It would be nice to run all of that, but then apply it to the simulation. We'll see if that's possible. But it's really hard to also make the code of the real robot work in the simulation. As you saw, and what I talked about, but I'll reiterate, I had to convert all the actions. Let's see where I created this. Save all actions to JSON. So I had to read all the actions that were in this SQLite format, D6A format. I had to then convert them to a list of lists, kind of pulse angle format, and then I had to convert them to JSON radian format. So even the simulation uses different servo angles compared to the real world. I have to create many different scripts to then convert between these formats. Here's the function to add a user debug text, which action, as you saw. Again, I'm looping through, the main simulation loop. If it's not the real-time simulation, we step, but if it is real-time, it's already automatically stepping at a real-time speed. And we're just setting joint angles instantly with joint motor control 2, robot ID, joint ID, position control with a specific gain, and the target position should be one of the, for the specific joint, it should be the radian position for a revolute joint with a force of 5 newtons. Hopefully that's somewhat understandable what I'm doing there. I have different helper functions for setting 0 for all the joints and stepping the simulation n times. Loading action files from this JSON format. I should show one of these formats, like hurdles.json. This is the pulse angle format, so every single servo. So the speed, first of all, we should do it in 800 milliseconds. All of these motions. So for the sixth servo, the servo ID 6, we should set the pulse PWM angle of 493. So when I read this, I'm reading the servo data and then I'm converting to the radian dict format, which looks more like this. So specifying angles with the name, it's much more understandable rather than servo IDs. I'm saying the hip roll should be 0.0, the right shoulder pitch should be 0.16. It's more understandable, but not the format that the real robot expects actions to be in, or even servo positions to be in. Okay, so that kind of covers a lot of fun scripts and talked a little bit forwarding inverse kinematics and pybullet and how to load many robots and the kind of interface to pybullet. Often we're just loading like a plain URDF and loading the robot URDF. We can get a lot of information from each single joint, dynamics info, the name, the mass, the friction, the local inertia, and here I'm able to finally just run these actions and convert from pulse angles to radian dictionary format. That's how I'm able to run the same actions that are run on the real robot, but on the simulation. So that's just like, there's a lot of information, so I'll just reiterate that step. So let's make Johnny in the simulation wave, and in the real world, let's make him wave too. You can't really see him. Same action in simulation as in the real world, but there's different kind of speeds at play there, which I could optimize at another point. But at the moment, I'm more interested in position control and just getting to the correct positions and whatever makes the robot not fall over. How can it be useful to develop in the simulation? Okay, so that's a lot of information. Now let's get to the inverse kinematics and the kind of culmination of what application I did here. Okay, so typically when we do kinematics, inverse kinematics, we can use, like if it's a 5 or 6 degree of freedom arm, 5 to 6 stepper motors, 5 to 6 servos, for example. You're often in trigonometry and pen and paper. So like you've seen this kind of inverse kinematics. Like robot, see any nice pictures here. You're kind of doing this kind of trigonometry to find, even in 2D, you're splitting things into planes and different splitting things into planes. So this is a planar robot, but then once you have multiple planes, you can then do things like this and work on one plane at a time, depending on where it's pointing, where the base angle is pointing. But as you get to like 6 and 7 degrees of freedom, it's an analytic solution. It immediately gets in the answer. But once you get to 5, 6, 7 degrees of freedom, it becomes harder and harder to do this. And you get multiple possible choices. I used to follow the QUT from Australia, Peter Cook, I think. He does good inverse kinematics, but just for a 2-joint arm, and you can use trigonometry to find what is, if you want to get to a certain, first you do forward kinematics, where is the end effector, the end of the arm, but also if you want to get the end effector to a different place, you can find the angles Q1, Q2 that represent how to get to a specific end effector position. As Wikipedia explains here, this is forward kinematics. So given the angles, where are all the parts of my arm or URDF or human or humanoid or arm? But inverse kinematics is also used to recover the, that's not a good way to describe it. It's just a forward and backwards kind of process. And you always often get to this point when you get to 7 degrees of freedom, there exists infinitely many solutions. It's like if I hold on to a door handle or to Johnny here, my hand is fixed, but I'm able to move my elbow to many different positions. So that's why there's infinite joint angles that will make my hand be at the target position. Many libraries cover this. I was even working with Fabric in 2019. And for a long time, I was against this numerical optimization approach, iterative optimization approach with jacobians, because it just felt like you're trusting too much optimization. Whereas when you have trigonometry that seems more mathematically sound, to get to a certain position, but the whole field has moved to this optimization approach. And especially for humanoids, you need a more general solution. It's not just a 5, 6, 7 degree of freedom arm. You're talking 24 degrees of freedom on Johnny here. So optimization based inverse kinematics. Now there is flaws with this, but it enables a lot of extra things that trigonometry doesn't enable. For example, if the target is out of reach, the robot can still try to get as close as possible to the target. And I'll show many examples. But let's begin really simple. So there's a thing called random descent. And what happens there is you just try a random delta, random addition to each single joint. You're given a target, of course, then get end effector. Let's forget orientation for now. Let's get end effector to xyz equals whatever, 0.2, 0.2. That's the task of IK. One way to solve it, try random resolve in loop. Try random delta on each joint. If better than best, it's the new best. Sounds so stupid, and how could that ever work? But computers are fast. That's why I put the haha. So let's run this. It's trying to get to the red ball. Maybe that's kinematically infeasible, or random descent is failing. We're going to have a new red ball target soon. Not bad. It's using the right arm. It's a bit shaky because we're randomly changing all the joints, and we're also using simulation as part of the inverse kinematics loop. Not bad. You can see that the error here is 9 millimeters. There's no self-collision again. 7 millimeters. Now, that's leaning a bit backwards and a lot of self-collision, but the point is it's 8 millimeters accuracy. So random descent works, surprisingly. I'm obviously only optimizing the right arm joints. So it's kind of like a classic single arm control. And there's no way to specify constraints in this optimization because it's purely random. I think you can like remove things that would self-collide, remove configurations that would self-collide. But you get the idea. So what is happening in this script? Let's open it up. We have this function for random joint delta, how much magnitude, and whether to use the legs or not. And we know that we're specifying the legs to be 0. And the main thing here is the deltas, getting a uniform. The max is the magnitude minus 0.1 to 0.1. We're getting a value between these, and for all the joints, which there are 25, the base link joint to body is just a fixed base joint, and the IMU isn't really a joint. I can remove these. Classic distance functions. You can get the position of, this is forward kinematics right here. You can get the position given the robot ID and the end effector index, which would be the right gripper, for example, the current position, and then use classic Euclidean distance to see what is the distance from the current end effector to the target end effector. And that's how we were calculating that number here, final distance to target. And we can apply the joint positions. That's why it's so shaky, the robot. We're applying and stepping the simulation in this optimization process. You can make sure that there's joint limits and we're not going over. For example, joints can go from minus pi to pi or a shorter distance. So we can specify that. We tried to do a lot of self-collision stuff, but it's really complicated. And seeing if a configuration is valid related to self-collision. But anyway, let's get to the actual optimization loop. We get the current joints. That's all the angles. Put them into NumPy. Get the best distance. This is the current distance that we began with. We copy the best joints. And here's the loop. Max iterations is 1000. We call that function we showed before. Get a certain joint delta, and we just add that delta to the current joints. We can check if it's a valid configuration. Apply the joints, see the distance. So that's why the simulation is moving with the inverse kinematics optimization. We can see the distance. And then, as I said, if the new distance is lower than the best distance, these are the new best joints, current joints, and distance improved. Did we get any of this printing? Yeah, so for example, a lot of prints here. So we began in iteration 1, 31 centimeters away. Iteration 5, already 28 centimeters away. 26, quite quickly, probably within 18 centimeters. 300 iterations, we're 13 centimeters away. We get kind of maybe stuck in a local optimum at 11 centimeters. For that specific case, we couldn't escape this optimum, or the actual target position was literally not reachable. And we can print this best solution, which joint positions for each of the arms. But it's because I'm trying to optimize the right gripper's end effector position. I think we're still changing the left arm's joints, but it doesn't affect the right arm's position, so we don't change those as much. And I can print the forward kinematics of the gripper. This is the XYZ position, orientation, and quaternions for 4 values, XYZ, W. And the final end effector versus position versus the target position, which was 4 centimeters in X, 18 centimeters in Y, 23 in Z. Hopefully that makes sense. I'm doing, again, all the common stuff we saw before, connecting the GUIs, adding the pybullet get data paths, setting gravity, that's important, setting the plane, loading the robot. I am setting fixed space to true here so the robot doesn't fall over in this crazy optimization. And you can print how many joints we have, but it's including the IMU and the camera and stuff, which aren't really that, they aren't joints really. And we can print, as we saw, we've printed too much now, but you can print all the joint names and their IDs and find the right gripper index or gripper. That is our end effector index. We can create this red ball as the target and set the GUI to 1, activate it, and for 10 different positions, num positions 10, loop true num positions. I like cursor auto-completing what I'm saying. You can specify the target position to be a uniform X between these, but not too low because you can't reach down. And the orientation is just default, no orientation needed. And we're actually resetting the position of this target marker every time. Printing the initial distance, starting random descent IK, 1000 iterations. Threshold is 1 centimeter. Once we get to 1 centimeter, we've considered to have succeeded in the optimization, and then we apply the best solution. But as you saw, we're in the loop. In the optimization, we are applying positions as well and stepping the simulation. That's why it's so shaky. And then we run the simulation for a bit. That's where there was a pause. And we didn't need to run it for that long. And print some numbers. So that gives an introduction to the problem of inverse kinematics, and even solving it in a very stupid but somewhat acceptable way. It actually kind of works, but there's better ways to solve inverse kinematics, and it at least introduces how you can solve it. Now, there's better ways. So there's this great blog. Let's see if I can link this properly. Fine. This is a great blog of basic inverse kinematics in mujoco from this guy. And he talks about many different ways to do it. How to get to a certain XYZ end effector. That's a nice picture here describing everything I'm talking about. Forward kinematics is getting from joint angles to end effector. Inverse kinematics is getting from a end effector position XYZ to, for example, 4 joint angles. That's a beautiful picture. The whole blog is amazing. Highly recommend it. There's many ways to do it. Gauss-Newton, gradient descent, and Levenberg-Marquardt. And let's look at gradient descent. A numerical approach, an optimization, iterative optimization-based approach to inverse kinematics. You iteratively adjust, so similar to the deltas from random descent. You slowly adjust each of the joint angles to reduce the error between the desired and actual end effector position. But we need the transpose of the Jacobian matrix to map the difference between the actual and desired end effector positions to the angles of the joint. So we need to create like a gradient of how changing each of our joint angles will affect that end effector position. And once we know in gradient descent terminology where we are on a hill and what is the gradient to get closer to the top of the hill, for example, or the bottom of the valley, we can walk a tiny step towards that direction using the Jacobian inverse. I think the Jacobian represents how changing our joint angles will affect the end effector position. So the inverse Jacobian represents how to change. We have to use that to then change our joint angles. And we always set a learning rate similar to its gradient descent from neural network terminology. You can take 2 large steps, which would not converge well. Also, 2 little steps might get stuck in local minimum. Steepest descent. And you just have to try different learning rates. So the kind of pseudocode for this, again, we're setting tolerances, step size, the current joint angles, and the goal pose XYZ. Let's forget orientation for a second. And we can find the error. And then while the error is above the tolerance, get the Jacobian, get the inverse Jacobian, and find the gradient. Alpha is not specified here, or maybe alpha is the step size, is unclear. And multiplied by the error. We're using the loss. Error is the same as loss. We're using the loss landscape to find the gradient of this loss landscape, and then taking a step in the direction of the gradient of the steepest descent gradient to get to a better error. Here, checking joint limits. There's a lot of problems with checking joint limits in optimization-based inverse kinematics. And our new error now is the goal pose. That's that Euclidean calculation. The goal pose minus forward kinematics of all our joint angles. Explained pretty well. I'm still a little confused, struggling to find the right language to describe why inverse Jacobian I mean, let's ask ChatGPT. I'll just copy all of this. Why do we find the Jacobian and inverse Jacobian? What are the intuitive ways to describe, ways to talk about these? What are they? As I said, I thought the Jacobian was how changing our angles will affect the end effector position, and then the inverse, or maybe that's the inverse. I might be getting mixed up. Yeah, that's kind of what I said. Robots joint angles to changes in the end effector position. Yeah, okay, so that's what I thought. And then it's the reverse mapping, of course. Yeah, so if you want the end effector to get closer to, you want the end effector to get closer to the end point. So the inverse Jacobian tells you how to adjust the joint angles to achieve that movement. And Jacobian is the tangent line. Still kind of struggle with the concept of the inverse. To get close, the end effector closer, to change the error towards the desired end effector pose. Fine. Anyway, I then took this and adapted this gradient descent based IK and put it into pybullet. Let's run that. Inverse kinematics. Let's see, seems a bit smoother. See, this is impossible for it to reach, but it still tries. 12 centimeters away, you can see on the bottom here. Let's try another position. So now we're using a more reasonable approximation. Right around the gripper. I think it's trying to get the green actually to the green gripper to the target. It depends which part of the green gripper, but here 0.1 centimeters after 100 iterations. That's pretty good. Goal reached on 127 iterations. So it works. Not everywhere, but it works. We get this jumping around because we're in our loop again. We're changing the simulation and changing the joint angles in pybullet and using pybullet's forward kinematics. So let's open this script. Similar stuff again and again, setting gravity, loading plane and AINX, finding the end effector index, which is the right gripper, specifying which joints are the arm joints that I'm trying to optimize, right shoulder pitch, right shoulder roll, right elbow pitch, right elbow yaw, and the right gripper. Do we really have only 5 degrees of freedom? Am I missing yaw? Let's go back to the random descent list here. Shoulder pitch, shoulder down. Yeah, I really just have 4 degrees of freedom in the arm. That's not the best. The right gripper is just the gripping mechanism, so it doesn't affect this optimization. Fine. We work with what we have. Specifying the leg joints and the gripper joints. And here I'm creating this gradient descent IK class. Again, specifying targets. And again in a loop, setting target positions. Resetting the target, initial joint poses, and running iksolver.calculate. How does this work in this class? For iteration and max iterations, get the current position, calculate the error, and the error magnitude. You can get an error in all x, y, z positions, so we need to get to a single number. And if we're below the tolerance, we've reached our target. Jacobian again. See how that's done. Pybullet has its own Jacobian function, I thought, or maybe not actually. Here we're not using it. Only using part of the Jacobian. And we're also doing this damped least squares approach. You have to add a bit of damping to, not to prioritize leg joints, but prioritizing to get away from joint limits, for example. I tried to do stuff with the leg joints previously, but right now I think it's disabled. And then we're doing the Jacobian inverse with this lambda square and changing the joints with a delta and a momentum and a speed and all of this. It's kind of similar to neural network terminology, optimization terminology, and we're printing our error every 50 iterations and stepping in the simulation. That's a flaw. Shouldn't be stepping in the simulation. Cool, so that's gradient descent based. It's better than random descent. And then I found this repo from Kevin Zakka, who I really like. He built the Robo Pianist stuff, and I'll show you. It's very amazing. Built Mink, which is a Python inverse kinematics based on mujoco instead of Pinocchio. I'm going to talk about that another time, but Robo Pianist is very impressive. To make 2 full hands play piano, and it actually is a real kind of simulated piano that can play this, and the goal of reinforcement learning with high dimensional control is to actually play the correct notes. Impressive. Anyway, he built mjctrl, this repo, which minimal clean single file imitation of common robotic controllers, so mostly inverse kinematics. And for example, it's a differential IK, Nullspace control, but it's very low level mujoco kind of stuff, and I had to convert it to pybullet. Or maybe I should just swap to mujoco. It's much more powerful and controllable, but much more difficult to get started. And operational space control. So I was doing a lot of diff IK, but then I moved to Nullspace. So let's see what I have here. And I swapped from using pybullet for jacobians and forward kinematics, so we don't have to step the simulation anymore. I swapped to using Pinocchio, that way things are much smoother. So let's run this script. And I have sliders. All right, so we're much smoother now. There's less crazy stepping within the optimization loop. The best error here, and move the target. This is the Kuka arm in simulation. And the target is this green square, green cube. I think it struggles to get to the center. I think there is actually a reachability problem there for the robot. But I'm really impressed by the smoothness here. Get lower. And very smooth. But there is just certain places it can't reach, and I'm trying to work out if it's an inverse kinematics problem or if it's actually a reachability problem, and Kuka has problems with getting to certain parts of its space. Like we're getting to 4 centimeters away here. Anyway, and it depends on the orientation as well. So I can enable orientation control. So I've enabled an orientation control by setting over 0.5. Pybullet doesn't have button toggles. Now I can change the orientation of this target. So now if I change the role, it tries to get also the orientation correct. But certain things are not feasible, or not currently the optimization is failing to get. We can also change this, the pitch. Change the yaw. Certain things are just too hard. Like that. Or maybe just need longer. No, this is failing. It's a red cube when we're failing. So yeah, orientation is very important. Orientation control, optimizing orientation, because you can pick things from above, you can pick things from the side, you can pick things from many different angles, and sometimes it's worth optimizing that a little. But not exactly. You might want a soft constraint on which direction you want to pick things. If you're picking things from inside drawers, you don't want to hit things above and below, so you have to go in at a certain angle. So orientation really matters there. X, Y, Z. And I'm actually printing the X, Y, Z of the target position as a debug parameter there. It's struggling to get to this. I wonder why. So certain places I just can't get to. Now if I turn off orientation control, should try to get there with any orientation. I haven't fully tested that. Nice. So how does this work? I had it to do there. Why is the robot so violent? Well, I fixed that by using Pinocchio in the optimization loop rather than pybullet stepping the simulation. So again, classic stuff. Enabling the GUI, gravity, loading. But here now that we're loading Kuka eWeb model.URDF, that's in the usual pybullet get data path. And we're loading it also into Pinocchio. So twice we're loading the URDF, but once into the Pinocchio library, which is what we need in the optimization robot Pinocchio. And there's only 7 arm joints. Kuka has 7. It's 7 degrees of freedom, so perfect for optimization based inverse kinematics. And the end effector index is 6, so 0 to 6 is the last joint. There is a Kuka with a gripper that I could try. to actually pick up things. But we're just testing things. So we have this Nullspace IK, but before we get to the details of that, getting the initial joint positions, current joint positions, creating the target cube, and we can specify the orientation. Let's remove some of these to-dos. It was violent before. We can get the values from each of the sliders in a loop here. And if orientation is enabled, it's bigger than 0.5, that slider. We can set the position of the cube, and if we have an orientation, we can then feed it to our try multiple seeds function, which inside is calling iksolver.calculate, but I was trying many different things of trying multiple different initial points, because just for certain positions, optimization based IK solves, and I'm working out if it's a reachability problem or not. So if goal orientation is none, we don't provide a goal orientation here. So let's try and understand Nullspace IK. I think it's quite complicated. I don't fully understand it yet, mathematically. This is the class, specifying all the different joints, tolerances, max iterations. Stuff comes up again. Also damping and integration and different gains, active joints. Calculate jacobians from the Pinocchio library, which is great, but only for the active joints. Get the current end effector pose with forward kinematics and frame forward kinematics, and you can just get it like this and return it. We can try to avoid the joint limits. And here's the main loop. Again, for iteration and max iterations. Get the current pose, get the error. Don't really like DX terminology, I might rename. And if we have a goal orientation, we can get a specific format that Pinocchio needs, W, X, Y, Z. Get it to our rotation matrix and then log tree it to get the error in rotation, and we add this to the optimization. Position error, orientation error, total error is the combination of both. Now, of course, as always, we're tracking the best solution. If we're converging, calculate jacobians, get a Moore pseudo inverse, which is often needed when things are 7 degrees of freedom. And we're applying this pseudo inverse to twist, which I think a better way to say it is maybe like a gradient, how we should change our speed. Twist is usually twist, gradient, speed of the end effector, different joint angles. And we can limit the gradient, so to avoid joint limits, as we said. And then there's this null space projection. We're getting deep into linear algebra here. And scaling the velocities, how many steps. And if we're going over, we kind of clip our joints to be below the joint limits. And then there's a lot of deep, complex maths in there, but on one level, we're just trying to find the best error and using the gradient with other different tricks and constraints. And the result is what you see here. I think it's keeping the same orientation. So let's restart the script not add the orientation. See if the, yeah, it's changing the orientation of the end effector no matter what in the beginning. Now I could specify if we can't optimize, at least try to reach it, get to the closest position, but I haven't specified that right now. Cool. Okay, what else is there to talk about? I showed orientation, and I would like to apply this null space control to Johnny or other humanoids in simulation, but step by step and getting closer. And really, the biggest problem here is how to deal with optimization and reachability error. Go as close as possible. Try multiple seeds. What is feasible? Now that's a bit complicated. And I kind of mentioned this. Still the last problem. Just making it robust enough. So I was like looking at Google images of Kuka here and putting in reachability, and I'm not sure if red here means it can't reach, but yeah, there are certain points close. There's like a side view, certain points that it cannot reach, and green is like very reachable, I'm assuming. Here's another example. Yeah, close to the robot. So maybe my inverse kinematics is working. It's a common problem with inverse kinematics of if it fails, what do you do if it fails? Again, they have these red circles here, which to me means maybe, yeah, the robot cannot reach these positions, but I'm not fully sure. I specify Kuka Iwa 7. I'm getting the same things. I could do a reachability analysis. So that comes to the next point. So I've done a reachability analysis with grid-based forward kinematics. So I'm like looping through all the joints with increments. In increments. I'm plotting lin range, num samples. I'm plotting side and top view. So I can show you for at least Johnny how this looks like, and I ended up creating some art. So I have this file called reachability analysis, and I'm like looping through all the joints with a certain number of samples. And this way you can actually see where is reachable. For example, here, creating this cool kind of snowflake art. This is only 5 samples per joint of all the places the right hand can reach. When I did 10 samples, I started getting more of this kind of beautiful art of all the places the robot can reach. That's forgetting self-collisions again. 20 samples, wow. Getting crazy. I can run this for you. So it's actually telling me how many days or hours this is going to take. This is only 5 samples, and we're using 59,000 points per second. It's a grid-based approach, and using specific arm joints, where will the right gripper end up? And I'm using streaming generators because you try to get to 40 points, it starts taking way too much memory and computation time. So let's see, that's way too fast. So if we do how many samples? Let's do 15. Tells me 759,000 points. Let's see it calculating here. Cool, you got the idea. That's reachability analysis to see where the robot can reach. But maybe that's just where I can reach. But I like what these images are doing here is specifying like what is a bit easier to reach and orient yourself around. You can try many different orientations for each X, Y, Z. Certain places are much harder to reach. Let's run the Nullspace on here again. For example, Y is, it can reach there, and then we get here. So it seems like it's kind of matching the image, depending on which side view. Yeah, so I just can't get on the inside probably. I was trying to follow a circle as well. Let's see if I can get that working. Just trying to do a simple task of a circle. I'm not sure if I have it here. Yeah, target position gets circular target. Do we have this function? And instead of reading target position from there, let's import this function. From IKUtils, get circular target. Will this work? So this circle, it's moving in a circle. Let's see if we get on. This was failing before by default. Yeah, we kind of fail here, but is it using orientation? No, it shouldn't be. Well, okay, fails here because it's just too close. But we'll succeed in a second once the cube finishes the circle, and we're back. Okay, let's make the circle a bit further away from where we're specifying the center. Let's make the circle further away. Four, 5. Maybe a bit lower. Let's see. Okay, that's already too far. Closer. Yeah, still just becoming kinematically infeasible for some reason. We're getting like 1.5 centimeters away, so we're getting close. It's just not to the tolerance. You see here, as we come back. Okay, now it's succeeding. Oh no, here's a failure. The error is 2.7 centimeters. I can build code to say that's good enough, but sometimes it's not good enough. Anyway, we've covered a lot, and let's get to why we're doing all this inverse kinematics based stuff, because this is the typical motion planning and control way of doing robotics. So it resulted in this mic drop application. So this is going to create a simulation with G1 let's see, it's grasping the cylinder, which I call the microphone, and we drop it. Let's run it again. I'm specifying a target for inverse kinematics, which is there, a bit of tuning to do that, and we're closing all our grippers bringing it to the side and dropping. I can even measure if the grasp was successful, if the cylinder's position is close as we're moving away, if the cylinder's position is close to the gripper's position. How does this work? Pick up object. So I've built a whole class here, scenario, and I can actually choose whether to use Johnny or G1. Different functions for whether it's Johnny or not, because G1 has those 7 degrees of freedom in the hand. I'm trying to optimize Johnny's gripper, we'll get back to that. And we're using gradient descent IK, but I might swap to Nullspace, what you saw with Kuka. And I'm creating all these objects, the table, different table heights for Johnny. Let's run this with Johnny. I have an arg parse parameter here. So it's a smaller table for Johnny. And I'm really trying to pick up this cylinder, but he's struggling. I might need some orientation control. That's why we should use Nullspace. And we're failing to pick up this cylinder, and because of friction, weird things happen there. So we failed. And that's due to many different reasons, but the simulation for the gripper is difficult. Anyway, yeah, smaller table for Johnny in the code. Different cylinders and cylinder heights and radiuses for Johnny, smaller. And measure, as I said, is the grasp successful by saying is the distance from the gripper to the cylinder as we're moving. Moving together, then it's correctly in the hand. And here's the full kind of main function. Opening the gripper, printing positions, choosing target locations, going to a pre-grasp position, setting the marker there so I can see where that is, running the IK solver, which is the gradient descent from Aliframe that I adapted from mujoco, setting the positions of the best solution, again opening the gripper, stepping the simulation many times, and then we're lowering from the pre-grasp to the grasp position, running IK again, stepping the solution, setting the positions, and then we close the gripper. And then I'm actually, instead of doing inverse kinematics, I'm just moving the right shoulder based on different names for each robot. Different string names of the joint name. So we can use the same variable. I'm just moving the shoulder away, stepping the simulation. And then we can drop the mic by opening the gripper. And that's the full application of inverse kinematics and why we do it. But as you see, there's problems and limitations, and we could make it better, or we can go full imitation learning, reinforcement learning. This is why people often give up on full motion planning and, oh, well, this is just so complicated, we should just learn everything. And there is pros and cons to doing that as well. All right, we covered a lot. I think next time I can show a lot of my progress on my visual servoing with ray trace, find cube and sock positions, increasing accuracy. We talked about in the real world how Johnny is becoming better at picking socks. And so many other things to discuss. Motion, retargeting, teleoperation. Done a lot of work on that. Okay, I think I'll just leave the stream there. That was quite long, but it's all here in my daylog. Today's Swiss stream showed you my t-shirt, Humanoids 2024, and the image of the robot on the back, and kind of put everything into context with this tweet from Jim Fan about how important simulation is. So we're using pybullet. Maybe another time I'll be using mujoco, but it's harder to get that up and running. URDF files don't work by default. You have to change them to mjcf or change things in your URDF. I've even done some work on reinforcement learning. Sure, let's leave it there. We covered a lot of information today.